then there is no sign bit. There is no sign bit in the number, in the binary number. So every bit should be inverted for one's complement. Every bit should be inverted for one complement. One should be inverted to 0. But for signed binary number, the 1 should be 1. Don't need to convert it to 0 because it is a signed bit. Right? Okay. Hexadecimal number. Hexadecimal numbers. We should remember this table. Remember this table. A, B, C, D, E, F. A, B, C, D, E, F. Four bit binary numbers could represent can represent 1 bit hexadecimal number. So we can divide the binary numbers into 4 bits for each group. This 10 is represent, it means the number 6706 3 is of decimal number. And this 16 is tell us the number is hexadecimal number. Octal numbers use symbols 0 to 7 to represent the numbers. 8 and 9 are not used in octal. So a binary number can be converted to octal by grouping bits 3 at a time and writing the equivalent octal character for each group. Okay, BCD code, binary coded decimal, is a weighted code that is commonly used in digital systems, such as clock display. Well, it is necessary to show decimal numbers. So we should know that each 1 bit decimal number can be represented by 4 bits of binary coded decimal. 4 bits. We should use 4 bits to represent 4 bit binary number. 4 bits of binary number to represent 1 bit decimal number. So 10 should be represented by 0001 and 0000 because there are 2 bits. There are 2 bits of decimal number. So, and the 15 should be represented by 0001 0101. 001 equals 1 and 0101 equals 5. 4 plus 1 equals 5. BCD. for 3-bit decimal number, BCD is 12 bit, except 100 decimal.
Yeah.
For 1 equals 0001, for 0
Yeah.
equals 0000, 0 equals 000.
Yes.
So
Yes.
12 bit. What is 12 bit?
12 bit. Yes. Yes. So, if we want to represent our decimal number using the BCD, we can find that this number, this BCD number, in fact, it is what? Our decimal number. Very easy. Each four binary number represent one decimal number. So this is what? 8. This is 3. 8, 3, 4 plus 1 is 5. 5, 9. 8 plus 1, 9. So the decimal number is 8359. So it is very easy. 8359 can a decimal number. Gray code. I didn't introduce this code in detail. We only need to know this code a little. It is an unweighted code that has a single bit change between one code word and the next in the sequence. Gray code is used to avoid problems in systems where an error can occur if more than one bit changes at a time. It is usually used in communication, in data transmission, because there are many errors can occur in the data transmitting. So this code can be used for this task. If you want to know this Greek code a little, you can turn to page 48. You can turn to page 48. 46, the Greek code. And ask two code is the code for alphanumeric characters and kanji characters. Okay, that's the important concept that we have learned in chapter 2. And now we continue to learn chapter 3. Chapter 3, logical gates. Logical gates. There are important variables. Boolean variable. It's very different from arithmetic variable. All variable is a symbol used to represent on action, on conditions, or date. Each variable Each variable has a value of 1 or 0. Has a value of 1 or 0 because this kind of variable is used to represent 1 bit of binary number. 1 bit of binary number. Please turn to page 61. The book didn't introduce this into concept. We can recommend it from the PPT. The first concept of variable. The second concept is the complement. The complement of a variable represents the inverse of a variable. The inverse of a variable indicated by an overbar. Thus, the complement of A is A overbar. Or we can represent this. The complement of A use this symbol. Or A overbar. They are equal. They are the same. The complement of a variable. Our literal is a variable or its complement. Literal is a variable or its complement. Boolean addition. Addition is equivalent to the OR operation. The sum term is 1 if one or more literals are 1. The sum term is 0 only if each literal is 0. For example, determine the values of A overbar, B, and C overbar that make the sum term of the expression A or B or C equals 0. Then A, what is the value of A? What is the value of B? And what is the value of C? Or what is the value of A overbar, B, and C overbar? According to the rules of OR operation, if we want to make A or B or C equals 0, what are the values of A, B, and C?
0, 0, 0.
Yes, 0, 0, 0. Yes. A equals 0. B equals 0. And C equals 0. Then, what are the values of A overbar?
1.
Yes. Because A overbar is the complement of A. So, it is 1. And B equals 0. And C overbar equals 1. Because it is the complement of C. So, the answer is C. Boolean multiplication. In Boolean algebra, multiplication is equivalent to the AND operation. The product of literals forms a product term. The product term equals 1 only if when each literal equals 1. When each literal equals 1. So what are the values of the A, B, and C? If the product term of A and B over and C over equals 1.
What is the value of A, B, C? A equal 1, B equals 0, C equals 0.
Yes.
A equal
Very
1, B
good.
equals 0, C equals 0.
Yes, very good. So if we want the product term A, B over and C over equals 1, the value of A should be 1. B over must be 1. And C over must be 1. So A equals 1, B equals 0, and C equals 0. Right?
Yes.
Listen. Do you know? Understand? Commutative laws apply to both addition and multiplication. For addition, the commutative law states that in terms of the result, the order in each variable are odd makes no difference. That is to say, A or B equals B or A. This is the commutative law for addition. And for multiplication, the commutative law says that
A equals B.
A and B equals B and A. And logical operation. This is the content of commutative laws. Associative laws. The associative laws also apply both addition and multiplication. For addition, the associative law states that when only more than two variables, the result is the same regardless of the grouping of the variables. For example, A or B and C, B or C equals A or B first and then or C. And then or C. This is for addition. For multiplication, the associative laws states that when adding more than two variables, the result is the same regardless of the grouping of the variables. So B and C first and A equals A and B first and then and C. So we don't need to write this. We don't need to write. If they equals A or B or C, and the law equals A and B and C. This is the second kind of law, and the third kind of law is distributive law. Distributive law is the factoring law. A common variable can be factored from our expression just in ordinary algebra. That is, A and B or A and C equals A and bracket B or C. B or C. The distributive law can be illustrated with equivalent circuits. For example, this is the OR gate, and this is the AND gate. OR gate, AND gate. B or C, then AND A, right? AND A equals X. The right circuit, AND gate, OR gate. So this is A and B. This is A and C. Then OR A, B, or A, C equals X. They are equivalent. This is the distributive law. Rules for Boolean algebra. Rules for Boolean algebra. The first rule is A or 0 equals A. The two, A or 1 equals 1. The third, A and 0 equals 0. We can turn to page 67. The AND gate, logical expression from AND gate, and page 60. Page 72. The logical expressions for the OR gate. So we see the PPT. Please see the PPT. The fourth, A and 1 equals A. A and 1 equals A. But A and A or A equals A. A or the complement of A equals 1. 7. A and A equals A. 8. A and A over bar equals 0. 9. A over bar and over bar equals A. 10. A or A and B equals A. 11. A or A over bar and B equals A and B. 12. A and B, A or B and A or C equals A and A or B and C. We all need to remember the last two equations. We only need to do the last two equations, and the other 10 equations can be deduced. Can be deduced easily. Why A or 0 equals A? Yes, because if A equals 1 or 0 equals 1. 1 or 0 equals 1. And if A equals 0 or 0 equals 0. So A or 0 equals A. Let us Rule 1. A or 0 equals A. This is all on all cases. Okay. If A equals 1 or 0 equals 1. If A equals 0 or 0 equals 0. So X equals A or 0 equals A. Rule 2. A or 1 equals 1. Because 1 or 1 and 1 or 0 both equals 1. Both equals 1. So it is very easy to understand. Rule 3. A and 0 equals 0. And because for the rules of AND operation, both inputs should be 1. Then the result is 1. Other, the result is 0. So A and 0 equals 0. Rule 4. A equals 1. A and 1 equals A. Equals A. For example, if A equals 0, then 0 and 1 equals 0. If A equals 1 and 1 equals 1. So we say A and 1 equals A. Rule 5. A or A equals A. Why? Please see this figure. If A equals 0 or 0 equals 0. Right? If A equals 1 or 1 equals 1. So A or A equals A. Rule 6. A plus A over bar equals 1. Why? Because A over bar is the complement of A. So if A equals 0, then A over bar equals 1. So 0 or 1 equals 1. If A equals 1, then A over bar equals 0. So 1 or 0 also equals 1. So the result is 1. Rule 7. A and A equals A. A and A equals A. If A equals 0, then 0 and 0 equals 0. If A equals 1 and 1 equals 1. So A and A equals A. Rule 8. A and A over R equals 0. Because if A equals 1, then A over equals 0. So 1 and 0 equals 0. If A equals 0, A over equals 1. So 0 and 1 equals 0. So A and A over equals 0. Verse 9, A over bar N over bar equals A. Because if A equals 0, then A over bar equals 1. Then A over bar and over bar equals 0. So A over bar and over bar equals A. If A equals 1, the same result can be obtained. Verse 10, this is a little complex. Or A and B equals A. Why? Do you know why? We have learned
Yes, sir. Because this.
We have learned the associative law, and the distributive law. We have learned the distributive law. So we know that A or A and B equals A and bracket 1 or B, right? We can write like this: A and 1 or A and B. It is right.
Yes, sir.
It is right. So we can use distributive law for this equation, for this expression. So it equals A bracket 1 or B bracket, right? And 1 or B equals what? 1 or B equals what?
Equal B.
Yes.
So it is
1 or B equals what?
B.
B.
Yes.
What?
1.
Equals 1. Do you know the rules? 2.
A plus
Rules
B.
2. Rules 2. So 1 or B equals 1. So the last result is A. The last result is A. So we can get the result A or A and B equals A. It is a little complex, but we can get the result use the truth table. This kind of table is named is named as the truth table. Truth table. It is a concept for digital electronics. The truth table shows the outputs from the circuit for every possible combination of A and B. In each case, the output from the OR gate equals the value of A. Thus, A or A and B always equals to the value of A. This is the circuit. This is the truth table. And first, the first column is A, the value of A. The second column is the value of B, and the third column is the value of A and B. The last column is the value of A or A and B. The possible combination of A and B, the possible combination of A and B are 0, 0, 0, 1, 1, 0, 1, 1, right? So 0 and 0 equals 0. 0 and 1 equals 0. 1 and 0 equals 0, and 1 and 1 equals 1. Then A or AB, then 0 or 0 equals 0. 0 or 0 equals 0. 1 or 0 equals 1. 1 or 1 equals 1. So we can find that the value of the fourth column equals the value of the first column. So A equals A or A and B. Rule 11. A and A over bar, A or A over bar and B equals A or B. A or B. This is a little complex. We can get the result only use the truth table. The circuits and truth table demonstrate this rule. The truth table shows the outputs from the two circuits are equal for every possible combination of A and B. Such, the two functions are equal. A and B is the circuit. First, this is A, the value of A, and then this is the complement of A over bar, right? A over bar and B is the output. The output of this AND gate is A over bar and B, and then A over bar and B or A is the last output. So the circuit is represents the expression of A or A over bar and B. Right? In fact, it is equivalent to OR gate. Why? Please see the truth table. This is the truth table. A, B. There are four different kinds of combination. A and B. So A over bar and B equals A equals 0. Then A over bar equals 1. 1 and 0
0.
equals 0. A is 0. A over bar equals 1. So 1 and 1 equals 1. Then A equals 1. So A over bar equals 0. 0 and 0 equals 0. A equals 1. So A over bar equals 0. 0 and 1 equals 0. So then A over B. Then 0 or 0 equals 0. Right? Then 0 or 1 equals 1. 1 or 0 equals 1. 1 or 0 equals 1. Yes. And A or B. 1 or 0 or 0 equals 0. 0 or 1. 0 or 1 equals 1. 1 or 0 equals 1. 1 or 1 equals 1. So the value of the fourth column equals the value of the first column. So these two expressions are equivalent. We should remember this rule because it cannot be deduced easily. Also, rule 12. It is more complex. A or B, A or C, and A or B and A or C equals A or B and C. It is more complex. We also can get the result by the truth table. And the circuit of this expression is first we should use the OR gate. Use this OR gate we can get A or B. And use this OR gate we can get the A or C. A or B and A or C. Use this AND gate. Then the result is the last output is the result of A or B and A or C. And this expression, the circuit for this expression is A, B and C. Use the AND gate, B and C. B and C, then or A, use this OR gate. So the circuit is this. And the truth table, we should use this order. A, B, C. A or B. A or C. A or B and A or C. Then B and C. Then A or B and C. Use this order to represent. And there are 9 different combinations for A, B, and C. For A, B, and C. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. In fact, it is the represent the decimal number from 0, 1, 2, 3, 4, 5, 6, 7. Right? 7. So there are eight different combinations not 9, not 9, 8 different combinations. 2 power 3. Right? 2 power 3. There are 8 different combinations. So A or B, 0 or 0 equals 0. 0 or 0 equals 0. So 1,
0,
1,
1,
1, 1, 1, 1, 1, 1, 1, 1, 1. Then A or C, A or C, A or C,
0,
1,
1,
1, 1,
1,
1,
1,
1,
1,
1, 1, 1, and then and 0 and 0 becomes 0, and 0
0,
and 0,
1,
1, 1, 1,
1,
1. Then
B6,
B and C,
0, 0, 0, 0,
1 and 1 equals 1.
1,
So, and 1 and 1 equals 1. The others are 0. The others are 0. Then BC or A. We find these 2 columns. 0, 0, 0, 0, 0, and 1, right? 1, 1, because the 4 numbers are 1, right? So we can find that 6 column and the 8 columns are equal, right? Equal. So we must remember that this expression equals this expression. So there are 12 rules about Boolean algebra, but we only need to remember rule 10, rule 11, and 12, rule 12. The other rules can be deduced easily, so we don't need to remember. We only need to must remember A or A and B equals A. A or A or bar and B equals A or B, right? And A or B and A or C equals A or B and C. Okay, the next, the inverter. We have learned this function in chapter 1. The inverter performs the Boolean or not operation. When the input is low, the output is high, and when the input is high, the output is low. So it is very easy to understand. The NOT operation is shown with an overbar. Thus, the Boolean expression for an inverter is x equals a over bar. X equals a over bar. On inverter application, this is the example waveform. If the waveform of A is like this, then the output
of x is like this. If a is high, the value of a is high, then the value of x is low. If the value of a is low, then the value of a is high. So the waveform is invert to a. Is invert to a. All group of inverters can be used to form the ones complement of all unsigned binary number. Unsigned binary number. The second gate, AND gate, the AND gate. There are two symbols, two circuit symbols for AND gate. The first is like this. The first is like this. Like this. And the second is the AND symbol. AND symbol like this.
0001. This answer is good.
The AND gate produces a high output when all inputs are high. Otherwise, the output is low. So we can get the truth table like this. Truth table. The first two columns are the inputs, and the last columns are the outputs. 0, 0. 0 and 0 equals 0. 0 and 1 equals 0. 1 and 0 equals 0. 1 and 1 equals 1. And we know A and B equals B and A. Equals B and A. And the AND operation is usually shown with a dot between the variables. Use a dot like this. Use a dot. But it may be implied. So we can ignore the dot. Ignore the dot. Thus, the AND operation is written as A and B, like this. The dot can be selected. The AND gate waveform, like this. A, the first is the waveform of A, and the waveform of B. Then the waveform of X, we can get the waveform of X like this. Note that on the yellow area, A is high, B is high, so the value of X is high. On the other area, the value of X is 0. The AND operation is used in computer programming as a selective mask. If you want to retain the 10 bits of a binary number, but reset the other bits to 0, you could set a mark with 1 in the position of the retained bits. For example, if the binary number 1010011 is ending with the mark 0001111, what is the result?
The binary number ended.
Yes. 0 and A equals 0, right? A and 0 equals 0, and A and 1 equals A. So What is the result? Vincent, do you know the result? We have learned rule 3 and rule 4. Rule 3 and rule 4. Okay, let us have a rest for 10 minutes. You can calculate this.